Yesterday we talked about equilibrium, and we're going to apply that to today's lesson. So first, let's just review what equilibrium is. This is when you have reactants turning into products at the same rate that the products are turning back into the reactants. So we show this with a double arrow, and it means that both reactions are happening at the same rate. Well, Le Chatelier's principle says that you can cause stress to the system, and we'll talk about what that means in just a minute. And you can force it to go faster in one way than another. And eventually it will reach equilibrium again, but for a small period of time, you can make one of the reactions go faster than another. And this can be beneficial if you're trying to produce a whole lot of the products. Once it's reached equilibrium, remember the numbers are not changing. So you want to kind of put stress on the system to make it go faster in the direction of the products to create more products. So when I say put stress on the system, there are three things you can do. You can change how much stuff you have, so you can change the concentration or the amount of the products or reactants. You can also change the pressure, and this one really applies mostly to gases. And you can also change the temperature. So you can just memorize all these different rules for which way things shift, but it's better if you can kind of conceptually imagine what's happening, because then you don't have to memorize all of this. So here's our system, and what I want you to do is to imagine that you're at the beach, and you have a sand pile, and somebody comes along and dumps a whole lot of sand. You have two sand piles that are the same height. Someone comes along and dumps a whole lot of sand onto one of the sand piles, and all you can do is to push sand either left or right to make it balance out again. And so in this case, you see how this one is really tall. In order to make them the same height, you would have to push sand to the right sand pile to make them balance out again. Whereas if you had a short one on the left and a tall one over here, you'd have to push sand to the left. So you always push sand towards the shorter sand pile. And this happens with reactants and products. So if you imagine for the reactants, so if the question says that you are increasing the reactants, that means this side is going higher, and the question would be, which direction is the reaction shifting? And again, it always shifts towards the lower sand pile. So in this case, it would shift to the right to balance it back out again. If the question said that you took away something, so they're the same height, and let's say that the question says that you're taking away products, so now you have a lower amount of products. Again, shift it towards the shorter sand pile. So since you took away some products, that side is now shorter, so it would shift to the right. If you add products, so this time you're adding products, shift it towards the shorter sand pile, it's going to go to the left. So if you can just imagine those sand piles, you can even use your hands if you need to and go up and down, always shift it towards the shorter sand pile, and then you don't have to memorize all the rules. If a reaction shifts to the right, meaning it's going faster in the right direction, it should be products, then in the reverse direction, that means you're getting more of the stuff on the product side. So whichever direction it's shifting, that stuff is going to increase. If it shifts to the left, that means you're getting more reactants. And again, all of these rules right here, add reactants, shift right, you don't have to memorize any of that if you can just picture those sand piles and just always shift it towards the shorter sand pile. All right, the next one is pressure, and this one's a little tougher. What I want you to think of here is two words, crowded and lonely. So I want you to picture a balloon, and it has all these little particles in it, bouncing around. And what happens is that first of all, this is totally personifying all of this. Particles don't have feelings. They're not really smiling particles. This is just how I picture it. We understand it, so I don't have to memorize it. So here are your little particles bouncing around in the balloon. If you add pressure, that means you're squeezing the balloon. What's going to happen is those particles are going to get squished together. And as they get squished together, they're going to feel more crowded. And so to relieve that crowded feeling, the reaction will shift towards the side with fewer moles. And when I say fewer moles, I mean, let's say we have, okay, I think that's balanced. So here are our coefficients that are multiple ratios. We'll put a 1 here so you can see that 1. That looks like an H. So we have 2 plus 1 is a total of 3 on the left. I'm adding up the coefficients, and then we have 2 over here. So again, you're pushing on the balloon. Those little particles in the balloon are feeling more and more crowded. So the reaction is going to shift to whichever side has a lower number of mole-to-mole ratios. So in this case, the product side only has 2 compared to the reactant side has 3, so it would shift towards the products. Now that's going to change for every reaction, which is why you can't just put that it shifts right or left, because it depends on the reaction. If you're removing pressure, so now the balloon is getting really, really big, now those particles are feeling lonely. They can't even see their friends all the way across that big balloon. And so they want to go towards the side with more moles so that they're not as lonely. So again, if they're feeling crowded, make it go towards the side with fewer moles. If it gets bigger, make it go towards the side with more moles. All right, the last one is temperature. And this one is tough because there's several different ways that they could tell you whether something is endo or exothermic. They could say the word endo or exothermic in the question. They could give you a reaction. Let's just rewrite that reaction that we just had. And so they could go ahead and put energy into the reaction. So they could say plus heat. And now you can see that heat is already in the reaction. They also could put it off to the side. So if I have the same reaction, a different way to say that this is exothermic because it's on the product side, that means it's coming out. A different way to say it is to put a delta H off to the side, and then they can change the sign on delta H. So we'll say this is negative 50 kilojoules. So the important part here is that negative. Negative means that it's exothermic. Positive means that it's endothermic. And I said that in the notes right over here. Negative heat means it's exo, positive means it's endo. And so what you can do is to physically put it into the reaction yourself. So if it's exo, that means heat is coming out of the reaction, so we're going to put it over here. If it was endothermic, we would put it on this side, and then we would add our reactants. So again, exo means it goes on the right, and either they'll tell you that it's exo in the question, they'll put heat in the question or energy in the question itself, or they'll put it off to the side with a sign, and the sign will tell you where to put it. And then once you put it into the reaction, you just treat it like a sand pile. So if heat is on the product side, like it is in the bluer one, as you increase the heat, that means the product side would be a higher sand pile, so you're going to shift it to the left to get it back over to the reactants. They should all have double arrows. If you're doing the red reaction, notice that heat is on the left side of the reaction because it's endothermic. So as you increase the heat, the reactant side is going to increase, and so it would shift back over to the product side. All of this will make more sense when we go through an example. So let's do an example down here. So each of these changes over on the left are different ways that you can put stress on this reaction. So the first thing says that we're going to add N2. So find N2 in the reaction. We're adding more N2. So if we think about the reactants and the products, N2 is on this side, so that sand pile is getting taller, so you're going to shift it towards the product side because that's a shorter side. So you can either write the word right or you can just draw an arrow. If it's increasing to the right, what that means is that everything on the right of the arrow is going to increase the concentration because it's going faster in the right direction, so it's creating more of whatever's on the right of the arrow. So in this case, NH3 is on the right of the arrow, so we're going to be creating more NH3. To create that NH3, we have to use up the reactants. So we're decreasing the amount of H2. And the reason they have this one crossed off right here is just because you're physically changing it, so you can't measure what's happening to it if you're also changing it at the same time. All right, let's look at the next one. When you see pressure, you want to think crowded, lonely. That's what it's talking about here. That will clue you into what you're trying to do. So crowded or lonely. We are adding pressure. So picture your balloon. If you add pressure to that balloon, those particles are going to start to feel crowded. So you want to go to the side that has fewer moles. So let's go ahead and add up our moles. There's nothing in front of the N, which means it's a 1. 1 plus 3 gives us a total of 4 on the reactant side, and then we have 2 on the product side. So 2 is a smaller number. So if we add pressure, it's going to go towards the smaller number. So in this case, it's going to shift to the right. If it shifts to the right, everything on the right will increase. So NH3 is going to increase because we're going in that direction, and these two will decrease. All right, the next one, we're going to remove H2. So picture your sand piles. We're decreasing this sand pile, which means it's shorter than the product sand pile, and always go towards the shorter sand pile. So we're going to shift it to the left, which means that anything on the left will increase. Again, we crossed off H2 because we're physically changing that, so we can't measure it. And since we're going away from the NH3, that one's going to decrease. All right, the next one says to add heat. And so before you can figure out what's going on with heat, you have to know which side of the arrows the heat is on, with the energy, which side you would put it on. And again, there's 3 ways you can do it. They might put it in the reaction for you. They also could use words to describe the reaction like endo or exo. And then finally, they can put it off to the side. And that's what they did here. This negative sign implies that this is exothermic, which means heat is coming out of it, or energy. So we're going to put heat on the product side, and then you just treat it like a sand pile. So if we increase this sand pile, the product side will be taller than the reactant side, and so it's going to shift towards the shorter side. So these two will increase, and this will decrease. All right, what I want you to do now is to pause the video, and I want you to try those last 4 by yourself. Go ahead and fill in all the arrows, and then play it and check your answers once I write these in. All right, now check your answers. NH3, when you remove that, it makes that pile shorter, so it would shift to the right. I'm sorry, you're adding NH3. We're doing this one right here. So adding NH3 makes it taller, so you shift it to the left. And that increases the reactants. Pressure is the crowded lonely. So if you remove pressure on the balloon, that means the balloon's getting bigger. So those particles are feeling crowded, so they're going to go towards the side with more moles, so they have more friends. And in this case, 4 is bigger than 2, which is why it shifts to the left. Removing NH3 is the opposite of adding, so go just the opposite of that one. And then removing heat. Remember, we put heat on the product side, so if we take heat away, that means the product side would be shorter than the reactant side, so you're going to shift it towards the product side. And your progress check looks just like this, except there's one more column over here where you're going to talk about K. So let me talk about K for this last column. So for your progress check, you're going to do arrows again just like this, and we'll go over the answers in class. The last thing is that you need to know that temperature is the only thing that will affect K. Remember, K is that fraction where you put products over reactants, raise them to the power of the coefficients, and it tells you whether you have more products or reactants at equilibrium. You can figure out what happens to K based on which way the reaction shifts with the temperature change. So let's go back up to this very last one in the chart, this one right here with removing heat. This one was shifting the reaction towards the right. So what that means is you're increasing the products and decreasing the reactants. So if you look back at our fraction here, we're shifting it to the right. So the number on the top of the fraction is getting bigger, and the number on the bottom of the fraction is getting smaller. And if you have a big number divided by a small number, it's going to be an overall value that's big. And so K is going to be pretty big here. If the other way happened, so if you go back up to this one right here where we added heat and it shifted to the left, when it shifts to the left, that means the reactants are increasing. And notice that reactants are on the bottom of the fence right here. So if you're getting a big number on the bottom, if you have a small number on top and a big number on the bottom, like say 1/10, the value of that fraction is going to be really small. 1/10 of a pi is pretty small. And so you can kind of figure out what happens to K based on which way it's shifting. So if the reaction shifts towards the products because of the temperature change, then K will increase. If it shifts towards the reactants, K will decrease. So in your progress check for this K, you're going to cross off all of these except for temperature. So that's the first thing. Whoops, that one shouldn't be crossed off. The only ones that will be affected by K are the ones that have temperature involved. And that is it for this chapter. But we'll go over this in class because I know it's kind of hard to learn this from the video. Good luck. I'll see you in class.